All right, so now what we're going to be doing is applying this to application situations. So like actual like real world situations, right? And we're just going to be again needing to figure out what our A value is, our B value, and our D value, and what they represent. Yeah, so let's just go through a few of these. So to tell you the truth, as we're going here, I think probably like 70% of the questions in these application ones end up being like some sort of Ferris wheel question, especially in 30-2. So just get ready for Ferris wheel questions. So in this question, it says a Ferris wheel has a radius of 8 meters and its center is 10 meters above the ground. A rider gets on a chair on the Ferris wheel at its lowest point and completes one full revolution. All right, so in 48 seconds. So now, what would be helpful? Like they never actually gave us this picture. I just added this after. Is to kind of sketch out what it is that we know, right? So they told us that the radius of this Ferris wheel is 8 meters. Okay, so that's 8 meters from there to there. Okay. Now, from that we can determine that okay, this thing must be 16 meters high, right? 2 times the radius would give you the diameter of this thing, right? Now the other bit of information was it says that and its center is 10 meters above the ground. So are you guys okay with saying this? If it's 8 meters from the center of it to the edge, right, for the radius, and then it would have to be another 2 meters to give me my 10 meters. So 10 minus 8 gave me how high this thing was off the ground. Okay, so this picture is very helpful, and I would really recommend when you guys read these ones, draw it out and draw your dimensions on it, kind of like I have here, okay, just to kind of get a reference. Because, yeah, these are going to be our main source of information. So now it says, sketch a graph on the grid below to show the height of the rider above the ground, y, over time, x, for the first 48 seconds. So that's one revolution, right? Label key points on the graph. So how you would do this, right? So if time is where we're starting. So I already have it done. I'll just kind of explain the points that we're throwing on here. So time is on the x-axis, right? So, you know, are we in seconds, right? So we got 2 seconds all the way up, or 0 seconds all the way up until 48 seconds, right? And can you see right when we got on that we'd be getting on at a height of 2? Okay, does that make sense? Well, yeah, right? Because that's here. Right, we're getting on at the bottom, so as time is going by this way, our height is at 2 to start. So that's where we're going to start. So it's going to be at the point 0, 2. So then you'd plot that point on your y-axis. That's your starting point. Okay, so yeah, so if that's 0, 2, then sorry, I forgot where I was at. I was talking to another teacher there. I think I was just talking about, you know, so we did that point. Now we'll move on to the next point. So it says the ride completes one full revolution in 48 seconds, right? So another good point to make on this plot, right, would be after 48 seconds, then we would know that it would end up right there, right? It would end up back where it started at 2 meters. So now we kind of have like the period of this thing from start to end. That's a good place to start. Now the next one that would be useful would be the peak, right? So we know this thing's going to start here, it's going to go up, and then it's going to go back down again. Okay, so if that's the case, then right in the middle, right in the middle between 0 and 48 would be 24. So that's got to be at time 24 that this thing is at its max height of 18, right? And we know it's at 18 because, well, if it was 2 meters from the bottom and the whole thing had a diameter of 16, then it's going to be 18 up at the top, right? So that's going to be my max height there. And then tell you the truth, once you have those 3 points, just knowing the way that these sinusoidal waves work, if this was our minimum or our bottom, and then it would go up and then it would come back down again, right? And then from there, what we could do is you could piece in some more information, right? So in between 24 and 12, we're going to be at, well, half of the height, right? So that'll put us at 10, because if we were at half of the height, that would mean that we're right there. Okay, so we're at that point. And then, so that'd be at 12 and then a height of 10. And then it would happen again when we were over here, right? So it's going to be between 48 and 18. So right in between those 2 points. So that's going to be at the point 36. Okay, you can kind of see that from symmetry too, that this point is halfway between these ones. Oh, these ones. Okay, and then again it would be at a height of 10. All right, so that's kind of it. So there's our sketch of it, right? If you were going to draw that out. Now it says state the amplitude, period, and equation of the midline for this function. All right, so let's do the amplitude first. So the amplitude, well, the amplitude, I could actually see this right from my graph, couldn't I? The amplitude would end up just being the radius. It would just be the radius of our circle, right? So that would be this. It's always actually going to be the radius of our circle if we get a Ferris wheel or anything else, right? Because think about it this way too, if we graph this, if I do my midline, so we'll do the midline now too, the line that cuts this thing in half. Your midline is at 10. Well, where else in our circle would it be at 10? Well, that would be right at the center of our circle, wouldn't it? Right from there to the bottom. That'll always be the case too. The midline would be right where, you know, this thing rotates around. And then your amplitude would be 8. So it would be from there to the top. You could also do that from the graph if you like, right? So I can see from 10 up until 18, we're going to have an amplitude of 8. It would be the same here, right? It would be going down 8. Okay, so we've done that. Now the next part says period. So we've done the equation of the midline. Sorry, I should say the equation of the midline should be y is equal to 10, right? That's that red line there, right? A straight line going across. So we've done that. The amplitude we said was 8. So now let's find the period. So the period of this graph is just where it starts making a pattern over again. So the period of this graph, they actually told us, didn't they? The period of this graph is 48. That's how long it takes to do one full revolution. So that's going to be 48 seconds. So the period would be 48 seconds. All right, done. That's it. So now, next one says, determine the function in the form y is equal to a times sine bx minus, and then they give us a number, but that kind of looks like a c value from before, plus d. Okay, so now it says where y represents the height of the rider above the ground and x represents the time after the ride has started. That could be used to model the height above the ground of a rider on the Ferris wheel described above. All right. So now, first thing that'll make our life a little easier, notice that the equation, or in the equation, the value of c was already given, right? So again, remember what c did. C shifted this thing. It shifted it to the left or to the right. And I can tell typically this thing should have started in the middle, right? Our graphs always started in the middle and then went up and then went down again, right? So this whole thing looks like it's been shifted that way. The good news is we don't even have to, I don't even care. I don't care how much it's been shifted that way. And in 30-2, we don't need to figure that out. So we just need to know that it has been shifted, but they've done that for us, right? Now, our a value, well, we found our a value already. So if I start writing this thing out, we could write it as y is equal to our amplitude, our a value is 8, and then sine, and then our b value, well, we don't know our b value yet, do we? So remember, b is closely related to period. So let's find b. So b, remember, this is on your formula sheet, is equal to 2 pi over period. So b is equal to 2 pi over 48, right? That was our period. We said that up here, 48 seconds. So then this would be b is equal to, well, pi over 24 would probably be the best way to write it. Okay, so you can leave it like this. So all I did there was just simplify the 2 and the 48 and left the pi, right? So that'd be like 1 over 24. So just pi over 24. So that's my b value. Or you could actually go pi divided by 24 and you would get approximately 0.13. So same thing. Okay, so if that's the case, then if I'm writing this out, then my equation here, right, I've got a was 8 and then sine, and now my b value is 0.13. All right, so I've got that, and then x, they already told us that it's going to be minus 1.57, and then all that's left is just to give our d value. So what's our d value? How much has this thing been shifted up? Well, we already said that, didn't I? It's really the equation of our midline there. The whole thing The whole thing has been shifted up 10, right? That's our D value, is how much the whole thing has been raised off the ground. So that's going to be our D. So that would just be plus 10. There you go. That's the equation of our situation we got going on there. The regular rise and fall of the ocean's water level can limit the times at which ships can enter and exit a harbor. On a given day, the depth of water in a particular harbor, D, in meters, can be modeled by the sinusoidal function, this. Just a bunch of stuff, right? So where T is the time in hours after midnight. All right, so like a T is going to be our X variable now, right? All right, so if a particular ship requires a minimum water depth of 13.5 meters to enter the harbor on the given day, the time at which it can first enter the harbor to the nearest hundredth of an hour after midnight is. Okay, so if we think about it, what we've been given here, D, is going to be our depth, right? And they're saying that this ship can't go in the water unless it's at this depth, right? So they've pretty much given us the depth that we need to find. And now we actually need to solve for T. Now the good news is that for us in 30-2, we don't need to solve for T algebraically, really ever in these cases. The only way that we're going to use for solving these things is going to be graphically. So what you would do here is we would graph two equations, right? We would graph the line, well, this, right? So we're just going to punch all of this into your calculator, just as is, or in Desmos is the one I had working there. And make sure, oh, the other one too, make sure your calculator when you're doing this is in radian mode. Maybe I'll show you that before we get going. So when you graph these things, if your calculator is in degree mode, you're going to get some really funny looking graph, and it won't look quite right. So what you're going to need to do is change your mode to radians and then graph it, right? So then you can graph it just as normal in there, just like this, 2.35 times sine, and then just the way it's written, okay? So then you graph your second line at 13.15. So then if you do that, it actually seems kind of intuitive too. So remember, this is time going this way, going across our x. This line, so that was 0 down here, right? And we can think about our tide as being like the lowest down here and then the highest up here. And can you see that this depth, that this line that we made here, right, would be the depth right at 13.15, which is the depth that it needs to be in before it can go in the harbor, right? So that boat can't go in the harbor until any time after right here, right? And the time is this. This is our x coordinate here. This is our time right there. So it has to wait until 4.278. And then what was our time measurement? Yeah, time hours, right? So that's pretty accurate. You wouldn't really write it like that. It would just say, well, maybe it's around a little bit, 4.28 hours, right? And then it's fine. So once it's over here, it has enough depth, has enough depth. And then again, if the question might have been, when does it need to make sure it left the harbor by? Well, then you would find this point, right? And say, okay, you got to make sure that it's not in the harbor anymore at this point, or else it's going to be hitting ground.